Every battery technology competing for commercial adoption faces the same fundamental test. How much energy does it store? How fast does it deliver that energy? And what does it cost per unit of both? Sodium ion batteries occupy a defined position on all three axes, and understanding that position precisely against established lithium chemistries determines which market sodium ion can realistically capture and which it cannot. Mass-produced sodium ion cells deliver gravimetric energy densities between 100 and 175 watt-hours per kilogram. Lithium NMC, the chemistry powering premium electric vehicles, reaches 250 to 300 watt-hours per kilogram. Lithium iron phosphate, the dominant chemistry for cost-sensitive EVs and stationary storage, ranges from 150 to 210 watt-hours per kilogram. The gap between sodium ion and lithium NMC is substantial and unlikely to close at the cell chemistry level. The gap between sodium ion and lithium iron phosphate is narrowing, and at the upper end of current sodium ion production, the two chemistries overlap. Volumetrically, sodium ion cells store 200 to 400 watt-hours per liter against lithium ions 300 to 600. A sodium ion pack storing equivalent energy occupies more physical space and weighs more. That trade-off is acceptable in stationary grid storage, where weight and volume are not primary constraints. It is a meaningful liability in long-range passenger vehicles, where both are critical. Where sodium ion trails lithium on energy density, it leads on power delivery. Sodium ion cells support charge rates that bring a cell to 80% capacity in 15 minutes, outperforming many lithium iron phosphate systems under equivalent conditions. According to comparative battery performance assessments, round-trip efficiency for sodium ion cells ranges from 92% to 97%. That efficiency range is competitive with lithium iron phosphate and positions sodium ion as technically viable for grid frequency regulation, an application that demands rapid, repeated charge-discharge cycles rather than maximum stored energy per kilogram. Against lithium-sulfur, a chemistry with a theoretical energy density of 2,600 watt-hours per kilogram, sodium ion is not competitive on energy density. Lithium-sulfur's practical cycle life of 100 to 300 cycles due to the polysulfide shuttle effect makes it commercially unviable for most applications where sodium ion currently competes. Against vanadium redox flow batteries, sodium ion delivers higher round-trip efficiency and greater energy density per unit volume, though vanadium flow systems offer a 25-year operational lifespan and 100% depth of discharge capability that sodium ion does not match. Vanadium flow battery costs of $500 to $800 per kilowatt hour compared to sodium ion's current $40 to $70 per kilowatt hour define their respective market positions clearly. In the current battery market, sodium ion has carved a distinct and defensible niche in 2 to 8 hour storage applications. Its cost per cycle is beginning to undercut lithium iron phosphate in regions with high lithium import costs, according to energy storage market analysis published by Bloomberg. That competitive position strengthens as sodium ion production scales and per unit manufacturing costs decline. Performance metrics establish where sodium ion competes today, but commercial deployment at scale demands more than competitive energy density and charge rate.